welcome back. We were discussing Fourier transform for functions with moderate decay in R, and then we have seen the analog of fair kernel in R. So, as we have seen that if f both f and f hat has moderate decay, then a reasonable amount of Fourier analysis we can do. So, let us first calculate the Fourier transform of a very nice function called the Gaussian. Let f of x is equal to e to the power minus pi x square. As you can see that it has a tremendous amount of decay. So, this function will look like, it will decay very rapidly when we go across the infinity. And now, if we want to calculate the Fourier transform of that, one of the standard technique to compute the Fourier transform of this function is via complex integration. However, we will do it in a different way. So, define f of xi, this is equal to nothing but f hat of xi, which is defined as minus infinity to infinity f of x e to the power minus 2 pi I x xi dx. Okay. So, what we have seen is that if I take f of 0, then this is going to be minus infinity to infinity e to the power minus pi x square dx. And what is the value for f of 0? So, this is how to compute this integral. Now, one can write that f of 0 square is minus infinity to infinity e to the power minus pi x square dx into minus infinity to infinity e to the power minus pi y square dy, which is minus infinity to infinity minus infinity to infinity e to the power minus pi x square plus y square, then this is dx dy. Now, this is an integral in R2. Now, if I change this integral into the polar coordinate, then this is going to be integral 0 to infinity integral 0 to 2 pi e to the power minus pi r square, then this is d theta, and then this is r dr by changing it into the polar coordinate. Now, if you put r square is equal to s, then 2 r dr is equal to ds. So, this one is equal to r dr is there. So, 1 by 2 0 to infinity e to the power minus pi s ds, and this is a radial function. So, the integral it is not dependent on theta, therefore, we will get a factor of 2 pi. So, this is equal to pi e to the power minus pi s ds. We know that this is e to the power minus pi s divided by minus of pi, then this is 0 to infinity. Now, at infinity this is going to be 0, and at 0, so this is minus minus plus. So, this is going to be 1. So, f hat at 0 is equal to 1. Now, if we calculate f prime of xi, this is equal to minus infinity to infinity. So, if I push the mod, then this is dominated independent of xi, because mod of f of x is e to the power minus x square, that is integrable. I can take the derivative inside, and then what I will get is that this is f of x, then d by dxi of e to the power minus 2 pi I xi x, then this is dx. This is equal to minus infinity to infinity f of x minus 2 pi I x e to the power minus 2 pi I xi x dx. This is what uh, is the derivative of now f of x is equal to e to the power minus pi x square. Then f prime of x, this is equal to e to the power minus pi x square into minus 2 pi of x. So, this is equal to minus I times infinity to infinity f prime of x e to the power minus 2 pi I xi x dx. Look at that, f prime has also very nice decay, because of the decay is of Gaussian is too fast. So, even if we are multiplying with x, then still we are going to get a function with moderate decay, much more than moderate decay. So, this is nothing but I times f prime hat at xi. So, this is equal to, we know exactly what f prime hat of xi, this is I times 2 pi I xi, then this is f hat of xi, this we have calculated before. So, now this implies this is equal to f prime of xi is equal to this is 2 pi xi f of xi. So, therefore, this is a minus sign. So, this implies that f of xi, this is a simple ordinary differential equation which tells that this is c times e to the power minus pi xi square. So, now what is the value of c? We know that f of 0 is equal to 1. Thus, what we calculate f hat of xi is equal to e to the power minus pi xi square. This is a very nice symmetry. If f is Gaussian, then f hat is also Gaussian, and it has appropriate decay as that of the Gaussian. So, this now what we would like to do is that we would like to look for some nice function space, functions which are defined from R to R or R to C, which has tremendous amount of decay, and then we will see that whether their Fourier transforms are also going to have decay or not. So, now what do we mean by rapid decay? Rapid decay means if I have a function f and then I am hitting it by a polynomial, still I do not lose the decay. So, let me define what is a Schwartz space. This I will denote it by this. This is all function f from R to C, such that f is C infinity. So, C infinity means it is a smooth function, that means the derivative of all order for f exists. So, f is C infinity and supremum over n mod of x to the power n f mth derivative. This is finite for all n m belongs to n. That means, not only f has very good decay, all its derivative they are going to have very good decay, rapid decay at the infinity. So, now what are this is called the Schwartz space, and example in some earlier lecture we have constructed a function which has continuous function with compact support, and there are many of them. Suppose the function with like this, and I will take smoothen at the end, both the ends. So, these are all the continuous function with compact support, means after a compact set this function vanishes and they are infinitely differentiable. So, if f belongs to C C infinity, can smooth f is in C C, a C infinity, and f has compact support. So, that means there exist what is the meaning of that? F is smooth means f of n exists for all n, and there exists a m such that f is equal to 0, f of x is if mod x is greater than m, greater or equal. So, outside a compact set it vanishes. As you can see that if I am hitting with any polynomial with f, then obviously for the large x, f is going to kill them, and inside that it is a bounded function on a compact set. Similarly, if I am looking at f prime, then f prime will also have compact support, and so this inequality is trivial to show. Second, of course, just now we have done f of x is equal to e to the power minus of x square. So, this also it decay at infinity is so rapid that even if we are having hitting this f of x with a polynomial, still this decay is going to dominate the behavior of the product with the polynomial at infinity. Okay. Now one thing one would like to point out at this point of time, suppose if I take a function f which is smooth, but only f has rapid decay, but the derivative may not have that kind of decay. Such cases may arise. For example, consider f of x which is equal to e to the power minus of x square by 2, and then I will take sine e to the power x square. Then of course, this what we can do is that the supremum over x mod of x n f of x, this is finite, because sin x is bounded by 1. However, if I take f prime of x, then this is going to be e to the power minus x square by 2 into minus of x into sin e to the power x square plus e to the power minus x square by 2 cos e to the power x square, then this derivative is e to the power x square into 2x. So, this is minus of x e to the power minus x square by 2 sin e to the power x square plus e to the power 2x time e to the power x square by 2 cos e to the power x square. As you can see that the first part has nicely behaved if I hit with a polynomial, but the second part has a growth of e to the power x square by 2. So, that growth, it goes to infinity much faster than any polynomial. So, obviously, there is no chance that it is going to produce a decay. So, this implies that f does not belongs to the Schwartz space. So, only with rapid decay at the function level is not going to guarantee that f is in the Schwartz space. What we need to consider that not only f, but also all its derivatives, they have rapid decay at infinity. So, this now once we have this, now we will be doing for next few lectures, we will be doing Fourier analysis on this Schwartz space, and this we will see that how well cubed this Schwartz space is corresponding to the Fourier analysis. So, now just what we have seen is so if f is in Schwartz space, then tau x f at y, which is defined to be f of y minus of x, also that is easy to see, because if we are dealing with mod of y n and then tau x f to the power m at y, if for a fixed x, if we are taking this is the supremum over y belongs to R. Now, if I take the tau x prime, then this is nothing but f prime at y minus of x. So, that is not going to change. So, this is finite. So, in this case, then tau x f hat at xi, this is going to be equal to e to the power 2 pi I x xi f hat of xi. Okay. And similarly, if f is in Schwartz space, then you define the dilation f delta of x is equal to delta times f of delta x for delta greater than 0 belongs to that is also very straightforward to see. If you make a change of variable, then what you are going to get a constant. So, if we hit that with x to the power n, because whenever you are, suppose if you try to get f delta prime at x, which is equal to delta times f prime of delta x into delta. So, now delta is a fixed number. So, there is no problem, the constant is going to be. So, what one can do is that one can show that this is y to the power n f delta of m at y. This is lesser or equal to some constant which is going to depend on delta and which is finite. And we have already know that if f delta has moderate decay, then f delta hat at xi, this is equal to f hat of xi by delta. So, this two relation is going to be very useful for us. Now, also what we have seen is that if f is in Schwartz space, then as our definition says f k, this also belongs to the Schwartz space. So, now if we look at f prime hat at xi, we have computed it before. This is integral over f of x e to the power minus 2 pi I xi x prime dx minus infinity to infinity. Now, this is equal to first part is f of x e to the power minus 2 pi I xi x minus infinity to infinity, then minus of infinity to infinity f of x e to the power minus 2 pi I xi x into minus 2 pi I into xi dx. This is nothing but this first part is 0 because f has rapid decay, then the other one which is going to come out to be 2 pi I xi into f hat of xi. Similarly, if I take the double derivative, so what I will get is that f prime hat f k of xi, this is equal to minus 2 pi minus of 1 to the power k 2 pi I xi k f hat of xi k plus 1. Okay, so, this what we have easily by integration by parts repeatedly. So, that is what we are going to get. Now, the question first we will see that if f belongs to the Schwartz space, then f hat is differentiable. That is the first thing we would like to see. So, our ultimate goal is going to be that not only f hat is differentiable, but it is smooth. The derivative of f hat exists of all order, and it also has rapid decay. So, that means ultimately we would like to show that if f is in the Schwartz space, then f hat is going to be also in the Schwartz space. So, towards this first to see that if f is in the Schwartz space, then f hat is going to be differentiable. That means, what do we need to look at? F hat of xi plus h minus of f hat of xi divided by h. So, this limit must exist, that is to show exists. Okay, so now first let us see intuitively how does it look like. So, essentially what is f hat of xi plus h minus of f hat of xi 1 over h, this is equal to 1 over h integral minus infinity to infinity f of x, then this one is e to the power minus 2 pi I xi plus h minus e to the power minus 2 pi I xi x dx. Now, as we can see that if formally if I say that this converges to minus infinity to infinity, if I can push the limit inside the integral, then what we can see is that f this is equal to f of x, then this is the derivative of the function e to the power minus 2 pi I xi x for a fixed x. So, this is nothing but e to the power minus 2 pi I xi x, then multiplied by minus 2 pi I x dx. Now, as you can see, if x is in Schwartz space, then x times f of x is also in Schwartz space. This suggests x times f of x belongs to the Schwartz space. Hence, this is nothing but this is equal to minus 2 pi I x f of x. If this is my function, then this entire Fourier transform at xi. So, what we need to verify that justify that we can push this limit inside the integral. Once we can justify ourselves this convergence pushing of the limit inside the integral, then we know that this uh, uh, exist. Therefore, we can get that f hat is differentiable. So, in the next lecture we will justify the reason that why we are able to interchange the limit and the integral, as well as we will show that if f is in Schwartz space, then f hat is going to be in Schwartz space also. Thank you.